Hello, I'm Albert Ang from PASCO Scientific. This is the ES9070 Coulomb balance experiment from PASCO. The Coulomb balance experiment consists of two primary components, the Coulomb balance itself and a slide assembly. In addition, there are several other components that will make up the entire experiment. Here we have a kilovolt power supply which will generate the 6 kilovolt voltage necessary to charge the spheres. We have a basic electrometer, the Faraday ice cage, a few charge producers, an accessory kit containing support tubes, conducting spheres, and copper rings. We also have a CD that contains experimental procedures and instructions, and of course, documentations and manuals. Now we are going to set up the Coulomb balance and attach the slide assembly to the balance in preparation for the experimental procedure. When the Coulomb balance is unpacked, the counterweight vane is fixed to the balance with a clamp on the index arm, which has to be unfastened and loosened. There are also tapes here and here and here which have to be removed. When you do that, once it's been removed, make sure the counterweight vane is swinging freely. Adjust the index arm so that the edge of the arm here is parallel to the edge of the platform here on the Coulomb balance. Using the supplied copper rings, attach copper rings to the counterweight vane so that it will be horizontal when you insert the conductive sphere onto the end of the rod. Make sure that you push the conductive sphere right in until it reaches the little ridge extension on the rod here. Then adjust the magnetic damping arm so that the counterweight vane is exactly in the middle of the air gap between the two magnets. Now we are ready to do the alignment of the torsion wire in the vertical direction. First of all, ensure that the torsion knob, turn the torsion knob until the 0-degree graduation is exactly aligned with the fixed mark. Then adjust the lower torsion screw until the mark on the index arm and the mark on the rear of the counterweight vane is aligned, like so. Bear in mind that in a laboratory condition, there might be air currents due to air conditioning or open windows or even the movement of people that will affect this. So you may have to take some time and allow the system to settle down before you adjust it too much. Okay, so once the marks are aligned, the system is now adjusted in a vertical direction. We will now do the similar adjustment and alignment in the horizontal position. To do this, extend the support arm, thus so. Turn the balance on its side. Use the support tube in order to support the conductive sphere. By moving the copper rings up and down the counterweight vane, adjust the copper rings in such a way that the marks are once again aligned. When this is done, you can remove the support tube and the counterweight vane should be horizontal. You have now completed alignment of the torsion wire in both the vertical and the horizontal positions. Bring the Coulomb balance back into its upright position. And we will now attach the slide assembly. The slide assembly is fastened to the Coulomb balance by using this plastic strip and the supplied thumb screws. If any of this movement has dislodged this counterweight vane, just do the fine adjustment to bring it back into alignment again. Take one of the conductor spheres included in the set and insert it into the tube. Insert the sphere into the vertical pillar and adjust the sliding platform until it reaches a distance of 3.8 centimeters, which is the distance of the sphere. Adjust the spheres until they just touch. Ensure that the spheres are both aligned horizontally and vertically. And once you are done, the marks are aligned, 0 degrees on the graduation, the spheres are stable, the Coulomb balance is now ready for the experimental procedure.
Hello, my name is Andy Spoon, and I'm going to continue where Albert left off in showing you the experiment procedures, data analysis, and maintenance of the Coulomb's law experiment. To begin with, we'll start off with procedure A. Procedure A involves us charging each sphere, moving the spheres to variable distances, and recording that distance and the torsion angle, which represents the force between the two charged spheres. So let's begin. First, I'm going to connect my ground connection from the far right port of my kilovolt power supply around to the back, the yellow ground port. All right. My second connection will be also a ground connection from the back of that same port, clipping to the Coulomb's balance apparatus. This will prevent any extra charges being built up on the apparatus that may interfere with our experimental results. And finally, I'm going to connect the sphere charging probe to my positive high voltage power supply. To begin, I'm going to hold my charging sphere on the very end so I don't induce any other charges in me that will interfere with our experiment. And I'm going to turn on the kilovolt power supply that I have already adjusted to be 6 kilovolts. I will keep this voltage constant through part A. I touch each sphere separately and immediately turn off the kilovolt power supply. I'm now going to slowly slide the charge sphere to a 20-meter separation between center to center of each sphere. This will create a repulsion force between the two spheres, which I will have to compensate for by adjusting my torsion angle. I'm going to adjust the torsion angle until my alignment notches have came back together again, showing me that the forces have been balanced. I will record this distance and my torsion angle as my first measurement in Coulomb's Law Part A in Data Studio later in the table labeled Distance versus Twist Angle. To continue on with the rest of Part A, I'm going to reset my sliding sphere to its maximum separation distance and use my ground connection from the Coulomb balance to remove the charges from each sphere. I will also go ahead and touch the table just to remove any excess charges that may be around us. I'm also going to adjust my torsion angle back to 0, allowing it to come back to balanced again. My next step will be to recharge the spheres with the same voltage as I used earlier. Turn off my kilovolt power supply and move my sliding sphere to 14 centimeters. We encourage you to run multiple trials for each distance of separation that you go to, just to reassure your continuity between your measurements. At each distance, we will adjust the angle so that the two notches align, and I will continue those two steps all the way through 14, 10, 9, 8, 7, 6, and 5 centimeters of separation distance, so I can fill in my table Data Studio later on in Coulomb's Law Part A. I'm now ready to begin Coulomb's Law Part B. In Part B, we will be adjusting our two spheres to the same distance of separation, but each time we will now be varying our kilovoltage. This time, I'm going to start off at 6 kilovolts as in Part A, but then I will show you how to adjust it to 5 kilovolts and then later on to 4, 3, 2, 3, and 2 kilovolts for each distance. So we begin by touching each sphere individually, as in Part A. Turn off our kilovolt power supply, and slide our charged sphere towards the fixed distance that we will be using throughout Part B, which will be 10 centimeters. As you can see as earlier, our two spheres repel each other, and we will use the torsion knob to adjust our spheres so our two notches are aligned again. And this will be our first measurement in Coulomb's Law Part B. To get our second, we are going to move them back, maximum separation. Return our torsion knob back to 0 degrees. Ground, remove the charges from each sphere. And this time, instead of putting 6 kilovolts on the charged sphere, we're going to adjust it down to 5 kilovolts. We're going to place 5 kilovolts on each sphere. Turn off our kilovolt power supply and slide our charged sphere back to 10 centimeters. You should notice slightly less torsion angle required to balance out this force. This is because we used less charge on each sphere. To finish Part B, you would go on and continue this for 5 volts, 4 volts, 3 kilovolts, 2 kilovolts, and each time resetting the spheres maximum distance apart and removing the charge from each sphere. We are now ready to begin Part C. In Coulomb's Law Part C, you will first find the torsion ratio between the force and the angle of the torsion knob. To do this, we are going to turn the Coulomb's balance back over on its side, as Albert showed us earlier. We will begin by supporting the charged sphere and placing the 20 milligram masses that are located in the accessory parts of the Coulomb's balance. I'm going to place one 20 milligram weight along the center line of the charged sphere. I'm going to slowly remove the support, supporting the sphere with my hand, and begin adjusting my knob to lift the sphere off of my hand. Once I have adjusted the torsion knob to supply enough force, you will see that the sphere is allowed to float freely. I'm going to finally do some precision adjusting to get my notches to realign and record my mass and my torsion angle into mass versus twist angle in Coulomb's law part C. This will allow me to find the ratio between my force on the sphere and the angle in the knob. To finish part C, I will complete this procedure with my 20 milligram mass, my two 20 milligram masses, which will be 40 milligrams, a 50 milligram mass, and also a 70 milligram total masses. And now for the final part of the Coulomb's law experiment procedures. In part 4, we have already looked at how to measure the torsion constant of the Coulomb's balance apparatus. And in this last section, we're going to look at how to measure the individual charges that you placed on each sphere. To do this, we must first begin setting up the kilovolt power supply that we used in parts 1 and 2. I'm going to begin by running the same cable from my port around to my ground in the back. And I'm also going to hook up a ground cable that I'm going to run through the same port to my basic electrometer ground. In this experiment procedure, we're going to be taking a charged sphere and placing it inside of the Faraday Pell. To start off, I'm going to go ahead and connect my basic electrometer, and then I will charge my sphere and place it in the Pell to get the voltage reading that I can use to calculate the charge on the sphere. It's very important to remember that when hooking up the basic electrometer to the Pell, the red probe must connect to the inside of the Pell and the black must connect to the outside. I'm going to go ahead and turn on my electrometer, set my scale to 100, and zero out my basic electrometer. I'm now going to take my insulated hanging charged sphere, turn on my kilovolt power supply. Holding only the end of the charging probe, I'm going to charge the sphere to the same kilovoltage that I used in part 1, which was 6 kilovolts. I'm now going to slowly drop that sphere inside of the pail and touch the side of my pail. That will then give me a reading on my basic electrometer that I will record so I can use it in calculating the charge on the sphere. Now, if you have a LRC meter available, you may also want to use it to go ahead and calculate the capacitance of the Faraday Pell. To do that, I'm going to take my same two banana cables, connect them to my capacitance meter, and hook them up in this similar fashion as I did my electrometer to my Pell. Turn on the capacitance meter, and this will now give you the capacitance of the Faraday Pell, which you can use in your calculation of the charge. If you do not have the capacitance meter, that is still acceptable because you can use the known value of the Faraday Pell.
In the data analysis section, we will be using the Data Studio files which are included in the Coulomb's Law Experiment CD in order to analyze the data that we had collected in Part A. Here you'll notice a screenshot of the angle of twist, which, as you know, is a measurement representative of the force between the spheres and the distance r between the spheres. The twist angle is represented on the y-axis and the distance is represented on the x-axis. Notice the relationship between the two values as a green curve. This graph represents the twist angle data, which is now plotted against the inverse of the distance squared. As you can see, the twist angle data is on the y-axis, with the inverse of the distance squared now being the x-axis. Observe that the relationship is linear, which validates the inverse square law. This graph shows the relationship between the twist angle, which we have learned before is a measure of the force between the spheres, and the voltage, which is a measurement of the charge on the spheres. The twist angle is plotted on the y-axis and the voltage on the x-axis. This relationship is expected to be parabolic, and we will now do a power fit using the standard Data Studio tools to demonstrate this relationship. Observe that the power fit does indeed show a power of 2 for the best fit, and this does validate the result that we were expecting. We will now use data collected from Part C to determine the torsion constant of the wire. In that section, we turned the balance on its side and used a variety of masses on the sphere, bringing the marks on the balance back into alignment each time using the torsion dial. The graph now shows the relationship between the twist angle and weight. This weight data in newtons is calculated from the masses used, which were in milligrams. The weight is represented on the y-axis and the twist angle represented on the x-axis. This relationship, as you can see, is approximately linear, as we would expect. Doing a linear fit using the curve fit tool in Data Studio does confirm this relationship. The gradient of the line represents the torsion constant K of the wire.
In this final section, we'll be looking at maintenance on the Coulomb's law apparatus, and primarily how to replace the torsion wire. To begin, we are going to loosen the set screws with the Allen wrench around the counterweight vane, and making sure to thread the wire in the direction shown. Do not tighten the screws. We are now going to use the Allen wrench to loosen the set screw one full turn on the bottom wire clamp. Make sure that you are threading the wire in the direction shown and tighten both screws. In step 3, we are going to remove the wire retainer by unscrewing it from the top of the apparatus, loosening each set screw one full turn and threading the direction, but do not tighten the set screws back into place. Step 4, we're going to thread the wire through the washer that was removed also from the top of the apparatus. In step 5, we're going to go ahead and lay the torsion balance on its side. This will allow us to pass the wire through the hole in the torsion knob. It is helpful to hold the thread against the small Allen wrench, pushing them through together as shown. Step 6, we're going to put the lower wire retainer back in position, sliding the wire through the slot in the bottom bracket. In step 7, we're going to screw the wire retainer back in place, allowing us to create some tension in the torsion wire. Step 8, we are finally going to attach the torsion wire to the spring balance by using the wire retainer clamp, pulling the spring balance with approximately a force of 4 newtons, and then tightening the thumb screw back into place. Finally, we can adjust the height of the pendulum assembly and tighten the set screws with the Allen wrench, and you are now ready to calibrate the Coulomb's law apparatus.